Hello, I'm John Doherty, and welcome to another video on the nuts and bolts of using PEST and PEST++. This video is about regularization, and before we start talking about the nuts and bolts of how to implement regularization or regularized inversion using PEST, let's just say a few words about what regularization is. Regularization is a mathematical term which describes whatever it takes, or the mathematical devices that we use to achieve uniqueness in solution of an ill-posed problem. And calibration of a groundwater model is an ill-posed problem. So we're seeking uniqueness, so that doesn't translate into correctness of the estimated parameter field, but we want something that is unique and that has certain desirable properties. And ideally, regularization gives us uniqueness coinciding with the attainment of those desirable properties. When we calibrate a model, then, we seek a parameter field that allows the model to make a variety of predictions, all of which lie somewhere near the center of their posterior probability distributions. It can be shown that there is only one parameter field which can do this, and therefore uniqueness and decision support utility coincide. So that then is the broad definition of regularization. Now let's get a little bit more specific and talk about Bayesian Tikhonov regularization, because later in this video, this is what we will implement using PEST. Let's start off with the green equation. So we'll just have a little bit of theory here before we move into the practicalities. The action of a model can be notionally described by this equation. A model operator acts on parameters k, we add measurement noise, and we get what we observe in the field. So, the action of the model on parameters plus measurement noise is what we observe in the field. Now, that assumes that the model's pretty good. In fact, most models are imperfect, and model to measurement misfit is not just a product of measurement noise. It's also an outcome of model imperfections, but normally we just lump that in with measurement noise just to be able to treat it with mathematical ease. Now, when we're working in a highly parameterized world, we normally try to achieve goodness of fit by minimizing a least squares objective function. So here's the objective function that we minimize. This term in brackets is the difference between what we observe and model outputs. This is called a residual, or the vector of residuals. And this objective function is a weighted least squares objective function. Weights are contained in this matrix Q, which is often diagonal. Ideally, Q should be equal to the inverse of the covariance matrix of measurement noise. So we can rewrite the objective function using this slightly revised equation. Now, the smaller is this objective function, the better is the fit. So, conceptually, I need to minimize this objective function to obtain a high level of model to measurement fit. The problem is, if I've got a lot of parameters, and I normally do when I'm calibrating a groundwater model, because I want to have enough parameters to provide a realistic representation of subsurface heterogeneity, minimization of that objective function will not give me uniqueness. So there's no regularization here. And even if minimization of that objective function did give me uniqueness, probably I'd be overfitting model outputs to field data. Overfitting often leads to the assignment of weird values to parameters, and they're then transferred to predictions, and I may incur a considerable amount of predictive bias. So now let's add regularization. When we had Tikhonov regularization, we actually minimize an objective function still, but that objective function now has two components. And I'm going to call those components the measurement objective function and the regularization objective function, phi m and phi r. And we normally multiply the regularization objective function by a factor beta squared. Normally we square it. PEST determines what this is. We normally square this factor, call it beta squared rather than beta, just to acknowledge we're dealing with least squares objective functions. So, the measurement objective function, the regularization objective function, a factor applied to the regularization objective function, which is actually calculated by PEST in ways we'll show in a moment. Add all that together and we have the total objective function. And this is what is minimized when we do Tikhonov regularization. The measurement objective function is defined in the same way that we defined the objective function previously. This is the weighted least squares, sum of weighted residuals, the sum of weighted differences between model outputs and field measurements. So the lower is the measurement objective function, the better is the fit. So the measurement objective function measures the departure of model outputs from field measurements. The regularization objective function measures the departure of parameters from their prior mean values. Well, actually their initial values that are used in the iterative inversion process, which should ideally be their prior mean values. So the higher is the regularization objective function, the greater the amount that parameters need to depart from their prior mean values in order to give us a good fit, that is, to lower the measurement objective function. So there's a trade-off going on here between the measurement objective function and the regularization objective function. At the heart of the regularization objective function is the inverse of the prior parameter covariance matrix. So this comes back to the prior probability distribution of the parameters. And by putting this at the center of the regularization objective function, we're saying, or asking PEST, should perturbations from the prior need to arise to give us a good fit with the data, that is, to lower the measurement objective function, let heterogeneity, let the patterns of heterogeneity conform as much as possible with what we'd expect based on hydrogeological knowledge of a site, as encapsulated in the prior probability distribution as expressed by the prior covariance matrix. Now, in practice, in order for PEST to calculate beta squared, and in order to protect us from overfitting when we've got lots of parameters, the user gets to set the target measurement objective function, or gets to set a target for the measurement objective function, and PEST will not reduce the objective function any more than that target. It tries to achieve this target with the lowest possible value for the regularization objective function. So the user sets the target measurement objective function. PEST then works out beta squared. It works out how to balance these two components of the objective function such that we achieve our target measurement objective function, if we can, with the lowest possible value for the regularization objective function. And this type of regularization is called Bayesian Tikhonov regularization. And its purpose, if we just want to put it in a sentence, is to fit, but do not overfit, model outputs to field measurements by perturbing parameters from their prior mean values to the smallest extent necessary, using spatial parameter patterns that respect the prior. So we then obtain, hopefully, a good fit with the calibration data set with a parameter field that is totally reasonable from a hydrogeological point of view. Now let's make this just a little bit more general, because one of the nice things about Tikhonov regularization is that it can exist in many forms. Bayesian Tikhonov is just one of those forms. But let's, before we leave the subject of what regularization is, just make it a little bit more general so we can see what Tikhonov does in its most general form. So here, once again, is the equation for our total objective function, comprised of the measurement objective function plus a factor of the regularization objective function. The measurement objective function is always the same. The lower is the measurement objective function, the better is the fit between model outputs and field measurements. Again, in PEST implementation of Tikhonov regularization, the user gets to set a target measurement objective function here, and PEST will not go below that target. The regularization objective function, however, can really be defined in whatever we think is the best way in a particular inversion context. So I've altered the formula for the regularization objective function slightly to reflect that here. HR I'm going to call regularization measurements. And here we have a regularization operator on the parameters. So all this general formula is doing is saying that I have in the back of my head, or I have quite explicitly, I define a preferred parameter condition expressed through these regularization measurements. This could be smoothness, it could be minimum curvature, it could be the desire that if heterogeneity exists within the model domain, it exists in one place rather than another. The regularization objective function is low when that condition prevails. It starts to rise, and hence there's a penalty on the total objective function if there are departures from that preferred parameter condition. So here I'm not talking about initial parameter values as with Bayesian Tikhonov, though that is a preferred parameter condition, but I'm speaking a little bit more generally. I need to define a condition for the parameters which on its own almost provides, or does or almost provides, uniqueness of parameters. And again, that may be smoothness or minimum curvature or simplest parameter field. However, I will tolerate departures from that preferred parameter condition in ways that I like, as defined by the way that this QR matrix, this regularization weight matrix, is defined. I will tolerate departures from that preferred condition in ways that I like if that's what it takes to give me the measurement objective function that I want. Again, I define the target. PEST works out beta squared to balance one objective function against the other. This will be as low as it can in order to achieve the target. PEST works out beta squared to make it so. So just in a sentence, general Tikhonov regularization. In implementing general Tikhonov regularization, we fit, but do not overfit, model outputs to field measurements. By perturbing parameters from preferred values or patterns, for example smoothness, to the smallest extent necessary in ways that are in accordance with our knowledge of the system. We thereby attain parameter uniqueness. We thereby attain decision support utility of the model which we have just calibrated. So now let's look at how PEST implements Tikhonov regularization. Let's look at a PEST control file in which regularization is implemented. And the first feature of this control file is that in the control data section of the PEST control file, PEST is told to run in regularization mode. So the PEST mode variable is set to regularization. Other settings for PEST mode are Pareto, prediction or estimation. But if we're running in regularization mode, PEST mode must be set to regularization. It is highly recommended, though PEST will not insist, that the PEST control file include a singular value decomposition section. This guarantees numerical stability in the face of an ill-posed inverse problem. Tikhonov regularization is normally numerically stable, but this guarantees it. Maxing, that's this first variable on the second line, should be set to a value that is higher than the number of adjustable parameters. Now we come to the observation group section of the PEST control file. Now there are two ways now to identify regularization groups. We'll talk about the first one now, and we'll talk about a new way shortly. In the traditional way of using PEST in regularization mode, any observation group whose name begins with REGUL belongs to a regularization group. That is, differences between model outputs or prior information outputs and their preferred values contribute to the regularization objective function and not the measurement objective function if an observation belongs to a group, an observation group whose name begins with REGUL. That's how they're identified as contributing to the regularization objective function. So the regul prefix denotes a regularization group. Hence, they contribute to the regularization objective function, and PEST applies the regularization weight factor. A regularization group, just like any other observation group, can and often should have a covariance matrix associated with it. Regularization groups can exist as observations. So here we have the observation data section of a PEST control file, and some of the observations which feature in this belong to observation groups whose names begin with REGUL. More often, regularization groups are assigned to prior information equations, but there's no reason why observations can't belong to regularization groups. Same principle applies. Differences between model outputs and measured regularization values contribute to the regularization objective function. The regularization weight factor is applied. More often than not, as I said, regularization, particularly Bayesian Tikhonov regularization, is implemented using prior information equations. Therefore, in the prior information section of the PEST control file, we'll have a suite of prior information equations, each one of which will be assigned to an observation group, which is also a prior information group, which is also a regularization group, identified by the fact that its name begins with REGUL. And at the bottom of the PEST control file, if PEST is run in regularization mode, there must exist a regularization section. This has 3 lines of variables. On the first line, the first variable is called phi_m_lim. This is the target measurement objective function. This is where you tell PEST the objective function you want to achieve, and PEST won't go any lower. The next variable is called phi_m_accept. Read more about this in the PEST manual, but normally its value should just be 1% to 2% higher than the target measurement objective function. So don't worry too much about what it does. Just set it slightly higher than the target measurement objective function. The third variable on the first line is called fracfim. Now this can serve a fairly important purpose. Here it's set to 0.1. So what that means is that when PEST calculates the target measurement objective function during any iteration of the regularized inversion process, it actually calculates the objective function as the maximum of phi m lim or fracfim times the current value of the measurement objective function, whichever is higher. So if the measurement objective function is very high, this is the effective target measurement objective function for that iteration. So this lends stability to the Tikhonov inversion process. Regularization is always visible as the measurement objective function is lowered in an attempt to achieve the target. Once the measurement objective function becomes low and 0.1 times the value of the current measurement objective function is less than phi m lim, then the target measurement objective function is phi m lim. The rest of these variables, read about them in the PEST manual. These settings are fine 99.9% of the time. An optional variable can be added to the second line of the regularization section of the PEST control file. The name of this variable is regContinue. If it's omitted, it's set to no continue. If it's present, it can be set to continue. Now normally, when we're running PEST in regularization mode, if PEST is able to bring the objective function down to phi m lim or lower than phi m lim, it will just cease execution. Its job is done. However, with regContinue set to continue, it doesn't cease execution. It will, if necessary, raise the measurement objective function back up to the target in an effort to make the regularization objective function as low as it can possibly be. That is maximum respect for preferred conditions. This can be useful in some inversion settings. And finally, there's this variable ADDREG. This can be set from 0 to 5. If it's omitted, then it's set to 0. So we can have different regularization groups that feature in a PEST control file. All of these groups, their names begin with regul, R-E-G-U-L, if we're adopting the protocol we're talking about at the moment for identifying regularization groups. All of these multiple groups each contribute to the total regularization objective function. A weight factor is applied to all of them. If ADDREG is set to 1 or greater, PEST can actually adjust relative weighting between those regularization groups in an effort to make the inversion process just a little more stable. I normally set it to 1. That gives PEST the ability to adjust inter-regularization group relativity of weighting just a little bit if required to help with stability. However, if you've gone to a lot of trouble to set the weights or the covariance matrices that you apply to regularization groups, if you've gone to a lot of trouble to set that in accordance with what you think the prior parameter probability distribution is, then set ADDREG to 0 and don't let PEST fiddle with relativity of weighting or covariance matrices assigned to each regularization group. It's your choice. Normally I set it to 1, but sometimes I will set it to 0 if I have gone to a lot of trouble to set that the weighting or the covariance matrices for the regularization groups in accordance with the prior parameter probability distribution. Now let's look at a new way of denoting regularization groups. This gives us a little bit more flexibility in how we name those groups. So here's the way we've just been talking about. A regularization group is identified by REGUL at the beginning. This takes away a bit of flexibility because we really then only have 7 characters to play with in naming a regularization group. Now, observation groups in PEST have to be 12 characters. Take away 5 for REGUL, we're left with 7. So we're losing a little bit of flexibility here. The new mechanism for identifying regularization groups is to write the string regul group on the same line as the name of the observation group in the observation group section of the PEST control file. This identifies it as a regularization group, and we can give full 12 characters to the name of this observation group, which is now a regularization group. Its name does not have to begin with REGUL to be recognizable as a regularization group. If we want to associate a covariance matrix with a regularization group, we simply, as normal, write the name of a file containing that covariance matrix alongside the name of the observation group. Now let's look at some utility programs which automate the process of adding Tikhonov regularization to a PEST control file. They automate the process of adding Bayesian Tikhonov regularization to a PEST control file. So here's a diagram of an existing PEST control file. PEST mode is set to estimation, so it's a vanilla PEST control file. There is no regularization present in this file. If we run ADDREG 1 or ADDREG 2, a new PEST control file is built, in which PEST is now run in regularization mode. The PEST mode variable is set to regularization, and there's a regularization section in the bottom of the PEST control file. Each of these utilities takes each adjustable parameter from the parameter data section of the PEST control file and puts that parameter into a prior information equation in which that parameter is made equal to its initial value, or the log of its initial value if it's log transformed in the parameter data section of the PEST control file. The weight associated with each of these prior information equations is 1. You may want to change that, or as we'll talk about later, more often you may want to introduce a covariance matrix in place of weights. But just to make things easy, when ADDREG 1 or ADDREG 2 adds these prior information equations, they are given a weight of 1. Each prior information equation is assigned an observation group, which is now a prior information group. That group is named by affixing the string REGUL underscore to the name of the parameter group to which each parameter belongs. So, parameter group name with the prefix REGUL underscore, then these new observation groups are added to the observation group section of the PEST control file. Now this is convenient but a little problematic. It means that ideally you should keep your parameter group names down to 6 characters in length. Recall, observation group names can only be 12 characters. If you add REGUL underscore to the front, then the observation group name will be truncated and you'll lose characters at the end here. If two parameter group names have the same 6 characters the same, Their names, once you prefix regul underscore, become the same, and you've lost one of those observation groups just because of truncation of its name. So this can be a little bit inconvenient, and if you use ADDREG 1 or ADDREG 2, try to keep parameter group names down to 6 characters or less. We'll show another option shortly. Now, a lot of the utilities that come with PEST, including ADDREG 1 and ADDREG 2, receive their information through the command line. If you want to see what information they require, just type the name of the utility at the screen prompt and it'll tell you. So if we type ADDREG 1, it tells us what it needs. Now we run ADDREG 1 with the name of an existing PEST control file and the name of the PEST control file that we want it to write. We don't have to put .pst here. If we don't, ADDREG 1 will automatically add .pst to the end of the name that we provide. If we run ADDREG 1 in this way, it reads the existing PEST control file and writes the new one. In doing so, it assigns a very low value to the target measurement objective function. You can change this if you like. It also provides fracfim with a value of 0.1. Now this is something that I actually often do if I'm not sure what to set the target at. Aim low, but because fracfim is set to 0.1, the target measurement objective function is always 0.1 of the current measurement objective function, as we talked about a little while ago. So regularization is still happening. ADDREG 2, similar to ADDREG 1, but we can supply more information through the command line. So if we type ADDREG 2 at the screen prompt, we see what we can tell it through the command line. More options here, some of which are optional. Let's now run it with command line arguments. Here's the name, once again, of an existing PEST control file and the name of the PEST control file that we want it to write. We run ADDREG 2, it reads the existing PEST control file, writes the new one. In so doing, we can provide the name, we can provide the values, for the target measurement objective function. We can provide the value that we would like to assign to fracfim. We can set reg continue to continue if we like. And we can assign a value to the up test min. Well, the value is automatically 20. We can assign a value of 20 to the up test min control variable in the control data section of the PEST control file. Up test min is used by PEST HP. This tells PEST HP that it must use at least, or it must devote at least 20 model runs to lambda testing model upgrades with different values of the Marquardt lambda and fractional journeys along the line of the upgrade determined by the Marquardt lambda, that it must do this 20 model runs during each iteration of the inversion process. This can be especially useful if we are implementing Broyden-Jacobian updating, which is done by setting this jack update variable to 999. So that's ADDREG 2. Now let's look at ADDREG 2a, which is very similar except for one vital thing. Here's our existing PEST control file. We run ADDREG 2a, we build a new PEST control file, but this time we use the regul group protocol to identify observation groups, which are regularization groups. So once again, one prior information equation is added to the prior information section of the new PEST control file. One prior information equation for every parameter, which sets that parameter value or suggests to PEST that the value of that parameter as a preferred condition is its initial value as listed in the parameter data section of the PEST control file. Observation groups, which are now prior information groups, are named after the parameter groups. We do not add the regul underscore prefix because we don't need to, because we're using the regul group protocol for identifying regularization groups. So there's no loss of final characters here through truncation. The entire name, up to 12 characters, is transferred from a parameter group name to an observation group name. Those observation group names are then transferred to the observation group section of the PEST control file. So to run ADDREG 2A, we can type its name at the screen prompt to see what it wants. We can now run it with information supplied on its command line. It reads the existing PEST control file, writes the new PEST control file, exactly the same as ADDREG 2, the only difference being, as I said before, that we use the new protocol for identification of regularization groups. Now there's normally one final step required before we actually run PEST in regularization mode to solve our inverse problem using Bayesian Tikhonov regularization. So here's a PEST control file written by ADDREG 1 or ADDREG 2. Here's a PEST control file written by ADDREG 2A. Normally, especially if we're dealing with pilot point parameters, we will add the name of a file containing a covariance matrix to lines of the observation group section of the PEST control file following the names of observation groups, which are regularization groups, which pertain to pilot point parameters. How to build those covariance matrix files is described in another video. See the video on covariance matrices, which is part of this nuts and bolts of PEST series of videos. And that brings us to the end of this video. Thanks for watching.